And what's the current view of the electron and proton? What's stuff made of? Well, the kind of thing you learn at school is that, or the sort of way we look at this thing is that electrons and protons as little particles, tiny wee things. And the simplest view of the atomic world is that you have three kinds of particles: electrons, protons, and neutrons. These are little point things. Protons are pretty heavy. They're about nearly 2,000 times heavier than an electron. So are neutrons, a bit heavier still than the proton. Protons plus charge, neutrons zero charge, electrons minus charge. And the way atoms work is plus attracts minus. So you end up with a neutral, so atoms tend to want to be neutral. So hydrogen's one proton, one electron. Helium has got two protons, but it turns out that protons would just repel one another because they're both positive. We need something to stick them together. And what the stablest form of helium's got two protons and two neutrons holding it together. So it's 4 times roughly as heavy as hydrogen. 2 protons, 2 neutrons, 2 electrons. Plus 2, minus 2, zero charge. Balance. Balance, balance, balance. Lithium's got 3 protons, 4 neutrons. 7 times the mass roughly of the hydrogen atom. Not quite, because there's binding energies involved. 3 electrons. And then you just go click, click, click. Lithium, beryllium, boron, carbon, nitrogen, oxygen, etc. Each has 1 more proton, and they're distinguished by having more and more of these particles. A little cluster. So the picture is a little cluster of electrons and protons with a cloud of electrons going around them. And depending on your model, you could say they're going around like planets. Little ball going, a little point going around. That's the simplest model. Next one up is, and it's quite a long way up, the next one up is quantum mechanics, where you say, okay, the electron's really a wave. So it sort of wavies around it. And it turns out that wave is actually a spherical wave. So it looks like a spherical bell. So it's sort of like the oscillation you get if you took a sphere and donged it. Does things like this. So it waves spherically. And those spherical waves are the solutions of the quantum mechanical electron around the proton. And actually the proton has a spherical bell shape as well. So the current picture is of these things is that they're sort of little particles, like little tiny dots. So that's the simplest picture. But it depends on which. So we have an idea of what these things look like. We can describe them mathematically in quantum mechanics as a wave. We can describe them. So we have a bunch of different theories which describe stuff. Quantum mechanics, so that's these things here. So in quantum mechanics, the electron's sort of a variable sized wave. It can be a big wave or a small wave, but in an atom it's roughly 10 to the minus 10 meters. It's 10 zeros and a 1 meters. In free space, it's roughly the Compton wavelength, 10 to the minus 13 meters. In the solid state, it can be a lot bigger. So it's quantum mechanically, it can be nanometers or even micrometers in size. So that's quantum mechanics, that the picture of the electron is it's sort of a wavy thing. Then, on the other hand, we have relativistic quantum mechanics. In relativistic quantum mechanics, here's the book by Dirac himself, who invented relativistic quantum mechanics. And what it looks like in relativistic quantum mechanics is one of them. A horrible equation. What the horrible equation means is it means that what the electron looks like is it looks like a little point thing that goes backwards and forwards very fast. Actually, it goes backwards and forwards at the speed of light. And this is first described by Schrödinger, I think. Anyway, it was described in German, so it's called a Zitterbewegung, which means in German, a zittering motion. So that's what it looks like in relativistic quantum mechanics. In Maxwell electromagnetism, electrons really just act like a point charge, and they're the thing that emits light. In quantum electrodynamics, they are a point charge which also emits light, so similar to the kind of idea that we're talking about with just a little point electron. So in the standard model, there are lots of these little point particles, like protons composed of point quarks, electrons point particle, muons point particle, tauons a point particle. There are gluons, which are presumably also point particles, or act like point, well, except they don't, you can't scatter from them very easily. So there's a whole bunch of these things that are all thought to be sort of point particles in these more advanced models. But the problem is, you know quite a lot about it. We know what they look like, and we can do experiments on these things where you can measure the size and shape of these things. I did one myself in the 90s, where I looked at single electrons coming through in a solid state, and I could measure the charge profile of those electrons and see that they were distributed over tens of nanometers, individual single electrons, sizes of much bigger than atoms, many hundreds of atoms. One electron was distributed over hundreds of atoms in 3 dimensions. So how does it do that? How does a little electron get bigger than atoms when, if you just have an atom, then the electron's perfectly confined inside the atom? How do they get bigger? But they do. You measure it. So the problem is you know an awful lot about what they do, but by knowing so much, you know nothing, because it's contradictory. You have this picture of it being a little point thing in one theory. In another theory, you have a picture of it being a wave. Another picture, you have a picture of it being a cloud. Another picture, you have it emitting light, coupling to light, and having a coupling to light. So these are different views of but the same electrons. So by knowing so much, you somehow know less, because you don't know. So which will the real electron please stand up? Which of these pictures that I'm telling you about how the thing looks in different theories is the correct picture? And of course the answer has to be that they all are. But then if they all are, how?
I was going to say all of them and none of them.
None of them are the whole truth. All of them, exactly. All of them and none of them. None of these pictures are the whole truth. To get to the whole truth, you have to understand how and why it does what it does. And only then can you really say that you really understand what's going on inside these elementary particles, which are the things that then compose atoms, which then compose us, that then compose the universe around us. And when we're coming back now to the quantum bicycle, we're talking about the quantum bicycle, we're talking about just one of those elementary particles, which is seen as being a point particle, and seen as being an extended wave, and seen as being all these different things. The question then is, how does that thing that I just showed you translate into all of those things that we just talked about? How can it look like a point particle, one thing? How can it look like a wave in another? How can it get extended? How does that all work with that quantum bicycle? And that's what the quantum bicycle theory is about. And that's what Darren and Innes and myself and Martin and Viv and all these people in that washing list there are trying to find a way of describing the whole thing, everything, how all of these changes can take place. Is that a good enough picture at the moment for what people thought electrons were, little point things with charge, as though they're spheres, hard spheres, which atoms aren't. They're sort of more like fuzzy blobs, but then they're sort of vibrating fuzzy blobs, which have, as I said before, this perfect oscillation, like a bell ringing, like music. Music, like harmony as well, because the oscillations are in harmony with one another. Perfect, beautiful, frictionless, eternal notes, like a note. And that's a very good analogy, actually, because the thing is vibrating, so it's like a sound.